Hello, my name is Kelly Caldwell and I'm the lead instructor at Stanley Community College's Instructor Training Center. This is going to be a lecture on one of the many modules in the different courses inside of Cisco Networking Academy. I'm going to cover many different items in these particular lectures, starting with CCNA, going possibly all the way through DevNet. But to begin with, one of the things I want you to know is I go with a good enough philosophy, and that is no lecture is perfect. So in other words, if you're in the classroom with me, we could be interrupted by a person knocking on the door, my phone could ding, your phone could ding. I'm not going to have perfect lectures, and therefore my recorded lectures will not be perfect. You may hear my phone ding, you may hear a phone call start during one of the lectures, and I'll pause the lecture and then start back over. I'm trying to give you a good enough lecture to help you learn the materials. I also want you to know if you are not taking classes at a Cisco Academy, in other words, you're watching these videos on my YouTube channel and you're not trying to participate in an actual Cisco Academy, I strongly recommend that you go to www.netacad.com, scroll all the way to the bottom to where it says Find an Academy. I'm going to put in here the state, city that we are in. So in case I am in Albemarle, NC, North Carolina, as you can probably tell by my accent. But you'll see here Stanley Community College, and if you click here, you would get the information on what courses we offer and how to get in contact with us and how to actually see our offerings. So if you are in an area and you would like to find your local school or Cisco Networking Academy, then go to netacad.com, scroll to the bottom, and do Find an Academy. I strongly recommend that you get involved in the Cisco Networking Academy because it is a wonderful, wonderful program. Last but not least, enjoy, learn, and grow. So enjoy these lectures, learn from them, grow. If you want to grow in the IT field, that's excellent. Or if you just want to learn new things, that's even better too. We hope these lectures will be useful for you and that you will be able to use them to increase your knowledge in the IT field. Hello and welcome to an Introduction to Networks version 7.02, Module 8 lecture. This is going to be a lecture on the network layer. So we moved our way up the OSI model from the physical data link layer to the network layer. And we're now at the layer where everything is pretty much software. We discussed back in our earlier modules how the data link layer consists of the MAC and LLC, or the media access control sublayer, and the logical link control sublayer, and that the logical link control sublayer talk directly to whatever network layer protocols that you are using or are going to use, which typically now is nothing but TCP/IP. Although back in the day, there were other networking layer protocols such as IPX, SPX that we would use. This particular module, we're going to look at what IP protocols are used and what IP is. We're going to look at the field and header fields of an IPv4 and IPv6 packet. We'll look at host routes. So in other words, how a route determines how to host, how a host determines how to route to different networks. And then we will look briefly at the actual routing table on a router. And that's a key point. Routers are layer 3 devices or network layer devices. Now, one of the things that confuses people about the network layer and the protocols at that layer, IPv4 and IPv6, is that at layer 3, we use what is called best effort delivery. So in other words, it is not IPv4 and IPv6 at layer 3, at the network layer, are not guaranteed reliable delivery. They rely on transport layer protocols to ensure reliable delivery. And we'll talk about that as we move up to the transport layer in a couple modules. But this also, as you'll see here, we've got two major protocols we use, IPv4 and IPv6. IPv4 is the older 32-bit addressing standard. IPv6 is the still fairly old, it's from the 1990s, 128-bit addressing scheme that we use. And what we have basically is what I've mentioned before, and that is the idea that each individual device has a layer 3 address, and in that is a logical address. So it could be, on this particular example here, the PC on the right could be 192.168.12.10. The one on the left could be 172.16.0.10. And these two would have different IPv4 addresses. That allows each one of these devices to talk to each other. In this case, we've got 32.11 and 36.5. Now be very careful. It's kind of, if you don't notice that this third octet here is different, you may think that they're on the same network, but they're not. You'll see it's passing it down, being encapsulated all the way through the different layers of the OSI model. It gets converted into ones and zeros, sent across the network to be routed to the destination network, and then eventually it will be de-encapsulated by the receiving host and passed all the way up. And that would allow communication between 192.168.32.11 and 192.168.36.5. So these two devices are on different networks. Now at layer 3, again, it doesn't know that it gets delivered. It just does best effort delivery at layer 3. So here we have the PDU, again, talking about how we're encapsulating on the sending side, de-encapsulating on the receiving side. And again, best effort connectionless delivery. In other words, by connectionless delivery at layer 3, we basically put it into the PDU, we send it down to the frame layer, to data link layer, and we hope it gets there. We're going to rely upon upper layer protocols. If we go back to our example here, we're going to rely on layer 4 protocols for guaranteed delivery. At layer 3, we just send it out there and hope it gets there. So in other words, again, when it comes down here, this is a key point. When it gets down to this router right here on the inner network, layer 3 doesn't guarantee that it's going to be delivered. Layer 3 makes a best effort to deliver it. In other words, it will get down here to this router when it gets all the way down here as ones and zeros. And once it's there, the router will do a route table lookup to see if it has a route to the destination. If it does, it will route it, and we'll try to route it through this inner network. If it doesn't, it will send an ICMP destination unreachable, but it doesn't then try to retransmit at layer 3. It relies on upper layer protocols to do that retransmission. So IP is connectionless, best effort. All right, so again, it just sends it out there and hopes it gets there. Again, we're routed as quickly as possible. If a packet is dropped, doesn't make it to the destination, at layer 3, IP doesn't care. It does not retransmit. It does not try to do a retransmission. You will learn later that it's taking care of at the upper layers again. It is media independent, which is very, very important, and why TCP/IP has become the de facto standard of the internet. And that is because it can run across copper Ethernet. It can run across copper serial, optical fiber. It can run across wireless. It can run across anything, microwave. Any of those can be at layer 2. It can be encapsulated. I mentioned this way back when we were talking about the TCP/IP protocol stack and the 4 different layers. You know, the application, transport, internet layer, network access layer, and how back in the very beginning when they made TCP/IP, they didn't specify any required layer 2 protocols. And so that's why TCP/IP is media independent. So let's look at the IPv4 packet. Now, the IPv4 header, as you will notice, has a large number of fields in it. In fact, this was one of the issues that was worked on when they developed IPv6, as you'll see here shortly. In the IPv4 header field, you'll see there's a version, in a header length, differentiated service control point, express congestion notification, explicit congestion notification bits, total length, all the way down to your source IP and destination IP. One of the key things I like to point out to folks is this time to live. I mentioned to you at layer 2, there is no time to live field. But at layer 3, you're seeing here in the IPv4 packet, this is a time to live field that every time a packet goes through a router, the TTL is decremented by 1. When the TTL reaches 0, that packet will be discarded. So that is a loop prevention feature that's available in IPv4 and IPv6. On down, we'll notice here as we move into IPv6, you'll notice that one of the problems we have with IPv4, first off, we're out of IPv4 addresses. The 32-bit address space is depleted completely. There are no more public IP addresses available to even hand out. There's also, because of that, there's been a lack of what's called end-to-end connectivity. In other words, because we're doing a process called NATing, which means we're taking private IP addresses in the 1918 range, which we'll talk about in Module 11. We're taking private addresses, using them on our internal networks, and then we're NATing or translating those addresses into public addresses. But because of that, you can't really find what host was using a private address once it gets out on the internet. Not easily anyway. There are ways, but it's very difficult. So lack of end-to-end connectivity and increased network complexity, because in some areas of the world, you're being NATed 5 or 6 times before you actually get to a public IP address. So because of that, they want to develop IPv6. So it's a new version born in the 90s. So it was ratified, I believe, in 1999. But it has a 128-bit hierarchical addressing field. It is displayed in hexadecimal, and we'll show you that completely in Module 12. But you'll notice that instead of the address space of around 1 billion addresses in a 32-bit space, we have 1 undecillion. So in other words, there is theoretically a single IPv6 address for every grain of sand on the planet. So there's plenty of addresses. That space, however, what they did is they said, we're going to have this space, we're going to have much bigger addresses, but we're going to simplify the header. So you'll notice here's the IPv4 header again with all of its fields. Here's the IPv6 header. Notice how much simpler it is, how much fewer there are, so this much simpler IPv6 header packet or header is designed so that it's easier for routers to de-encapsulate or to take this packet apart and put it back together. So even though we have 128-bit addresses, one of the things that's been found is that with this simpler IPv6 header, routers and switches, well, routers and layer 3 switches can actually process this header faster than it did or they do IPv4 packet headers. And that was one of the design goals. Now you notice here, there are some of the same fields available. Hop limit is the new name for the time to live field, TTL field. So hop limit is the same as the TTL field. So it still exists in an IPv6 header. So again, much simpler, much easier for devices to tear apart, look into, and work with versus an IPv4 header. Still, it is available and usable, but it is a different header. Now let's look at how hosts make forwarding decisions. So most people don't know this or don't have an idea that a host has a routing table. Every host has a routing table. So I'm going to bring mine up here for my PC. All right. So on my PC here, I issued the command route print, and you will notice that I have a routing table associated with my PC. This particular PC is on the network 10.102.10/24. That, by the way, is a private internal address. You'll notice that I have the actual IP address of my host is 10.102.10.62. So this is on link and tells me that that is the interface there. So this is how my router or my device knows what network it is on. It would actually take its configured IP address, which is 10.102.10.62, and its subnet mask to it and find out that it is on the 10.102.10 network. Now, there are other IP addresses here. Some of them are PIPA 169.254 addresses. Some of them are multicast addresses, but each and every single device or host has a route table or a routing table. Inside of the routing table are going to be a listing for the IP address that's on that PC. So for instance, on this PC1, if I did a route print, you would see 192.168.10.10 with that 255.255.255.255. Let's come back over here. So in other words, I would have seen the 192 number for that example we have. You also notice, folks, I do have actually IPv6 routes. So IPv6 is turned on here. All of these are linked local addresses, but I do have IPv6. So there's a routing table on my device for both IPv4 and IPv6. I have a default gateway, and the default gateway is always the IP address of the router port closest to your PC that's on the same network. So on mine, you will see that I do have a gateway set, and that gateway is 10.102.10.1, which is on the same network as my PC, 10.102.10.62. Okay. In this example, PC1 would need its default gateway set to 192.168.10.1 or the port for R1, so that anything that wasn't local, it could send to the router and then allow the router to make a routing decision. So when a host routes to the default gateway, it's going to look for, if it's a local device, what it will do is it will try to send it directly using the host routing table. So in other words, with a route print or netstat-r, you could see the routing table for this PC1. And you will notice if it wanted to send anything to a device that is on the 192.168.10 network, you can see that that is local. It's already on the interface 1010. So any other device in the 192.168.10 network, it could send directly to. However, there's also this quad 0 route, which is a default route, which says anything that's not in this routing table, and there's some output omitted, obviously, because you saw how long mine was. Anything not in this routing table that I can't find a destination to or a way to get to it, send it to this default gateway. And that's what is made or what is meant by a default route or a default gateway. We go to this router, and then that router is responsible for trying to find a destination. Remember, though, it's best path, so our best effort. So PC1 would look in this local route table, decide that a remote host is over here somewhere, send it over to the 192.168.10.1 address and say, hey, you handle it, you take care of it. And then this R1 would look in its routing table and would make a decision about routing it and would try to forward it to the next hop. It's not always going to be successful. And if it isn't, it's going to rely on upper layer protocols to do a retransmission. So looking at a router, routers make routing decisions based upon their routing table. So here we have an example of the 192.168.10.10 PC1 sending something to a destination IP address of 10.11.10. Well, obviously, that was not in the routing table for 192.168.10.0. So it looked, found that default route or the quad 0 route going to the default gateway, sent that over to R1. R1 has to look in its routing table and make a decision and say, hey, I can get to the 10.1.1.0 network by sending it over to R2. It would then send it to R2, and R2 would have to do a lookup. And R2 would have that as a directly connected route right here. So every hop, the router takes the packet apart up to at least layer 3, makes a routing decision, and then forwards it. So it de-encapsulates it and then re-encapsulates it. One of the things you'll learn down the road is that routers make their routing decisions based upon their local routing table only. And just because there's a route to the destination doesn't mean there's a route back. So it would be possible for this to actually get routed over to the 10.1.1.0 network, but not have a way back to the 192.168.10 network. And we'll learn much more about that as we move into the next class, or the switching, routing, and wireless essentials class, which is CCNA 2. So in a routing table of a router, you're going to have what are called directly connected networks. And those are the networks that are connected and they have an IP address on that network. So in R1, it would have two directly connected networks. It would have the 192.168.10 and the 209.165.200.224/30. So those would be the two connected. And it may have remote networks. So that could be this 10.1.1.0, which it did have because it had this right here. And it could have what's called a default route. So even routers can have default routes, so that if something's not found in their routing table, they will forward it to a router that can then make a routing decision for them. So in this instance, R1, anything that's on the internet, R1 should have a default route that sends that traffic over to R2, and R2 will probably have a default route up to its ISP, and it will forward anything that's destined for the internet. Now, you can learn routes in two ways. One is they can be manually placed into the route table, and we do that with static routes, or dynamically, which is with dynamic routing protocols. So with a static route, we could go into R1 and make an actual route that says a route to get to the 10.1.1.0 network, go over to it, send it to 209.165.200.226. And if this link was up and running, that would go into the route table, and R1 would then be able to forward any traffic destined for the 10.1.1.0 network over to R2. R2 would have that 10.1.1.0 network as a directly connected network off of its interface on the right here. The problem with static routing is if there's a change or there are multiple paths, you would have to rewrite your static route. Now, obviously, this example right here is perfect for static routing because R1 only has one path to R2. So that's perfect for static routing. If there are multiple paths, however, you can do a thing called floating static routes, but typically when we start getting multiple paths, we want to use dynamic routing protocols, which allows the devices to share their connected networks and explain what networks they have reachability to. So in this case, if we're running a routing protocol called OSPF, the devices R1 and R2 would let each other know. So R1 would say, hey, I can get to the 192.168.10 network. R2 would place that in its routing table and say that network's available via R1. R1 would say, hey, or R2 would say, I can get to the 10.1.1.0 network and would tell R1, and R1 would put that in its routing table. Dynamic routing, the good news is it's automatically can recover when a link is taken down, or if there's multiple links and one of those links goes down. The negative can be it does take processing on the router. It also can be misconfigured, and it's not quite as secure as static routes. So here's an idea where we can see that this was the best route. And if we were running a dynamic routing protocol, if this link goes down, R1 can automatically create a new best path going through R3. There's a video here in the curriculum that you can watch, so you can take a look at that. And then here, we're just going to show you a routing table. This routing table for R1 shows that R1 is directly connected to the 192.168.10 network. That's what this C means, connected. These L routes are local link routes, which are only found in iOS 15 or higher. That tells you the actual IP address that is on that network and what interface it's on. So in this case, 10.1 is on gigabit 000. We're also connected to the 209.200.224/30 network. That is shown right here. And then we have an OSPF route. So we've learned via OSPF about the 10.1.1.0 network, which is available over on R2 because it says via 209.165.200.226. So this says that R1 learned via OSPF, and we can see that by looking up here, OSPF shown on the route table, learned via OSPF that this network is available over on R2, and it would send anything destined for that to R2. And then also we do have what is called a default route or quad zeros. It says anything I don't have a route to, send that over to 226, and then R2 will have to figure out what to do with it. The important thing about this particular chapter, we're going to go over those concepts a great deal more as we move forward in our journey together to learn CCNA. But the big thing here is at layer 3, it is a best effort delivery, connectionless delivery. IPv4 is our older standard layer 3 protocol that uses 32-bit addresses and is pretty much all addressing has been exhausted. IPv6 is 128-bit addresses, and it is the newer version that will be implemented in almost everything as we move forward. And then every device has some type of route table that it uses to make a decision about how to send things at layer 3. Hosts have host route tables, routers have routing tables themselves. I hope this has been useful, and you'll come back and we can discuss address resolution in Module 9.